Great. Thank you, Christine, for inviting us to speak today. My name is Paul Holowati. I'm the Director of Sales for Velo 3D in the Midwest.
Good afternoon. My name is Kyle Harbaugh. I am a technical business development account manager for Velo 3D, also in the Midwest. Paul and I work extremely closely together.
And so today we'd like to talk about large format metal AM printers, laser powder bed fusion, and how we're revolutionizing mission critical manufacturing. To give you a little background on Velo, Velo was founded in 2014 by Benny Buller. You see a photo of him. Behind him is the Sapphire, our first metal 3D printer. What's unique about this, and what's unique about our company, is this is a fully integrated metal AM solution. What I mean by that is we've got our own proprietary slicer on the front end, our equipment with nearly 1,000 sensors, and on the back end, we've got our quality validation software. And Kyle will get into this in more depth. And what we really focus on is delivering complex, high-value metal AM parts that no one else can build. We went public in 2021. We've got sales and support worldwide. And what I think isn't talked about enough is that we are a US company and we design our equipment in the United States, in Campbell and Fremont, California. And these are some of the industries we currently work in and some of the companies. A lot of the companies we work with, we're not able to mention their name due to defense or proprietary reasons. But SpaceX is a big customer for us. They've got over 26 machines on the floor right now. They were our first customer. And we're heavily involved in the space industry, but we're not a space company. We do a significant amount of work in defense, and more recently, in the last 2 years, in automotive with high pressure die cast tooling and injection molding tooling inserts. One of the differentiators I think that Velo does is our contract manufacturing network that we have set up. So what we realized early on that for Velo to print parts ourselves for customers, we're actually competing with our own customer base, and that's not where our focus is. So we set up a contract manufacturing network of companies that use our equipment, companies that are CNC shops that know metal. And any one of these companies can process a part from beginning to end at their facility and ship you the end part. They're very qualified shops, and we work with them very closely. In fact, we even have a team of engineers set up to look for opportunities for metal AM, and we drive work towards those contract manufacturers. It works out really well. So if somebody's interested in our technology, doesn't have the funds for a machine, they can utilize our contract manufacturing network. And as that increases, they may buy a machine. So the next slide shows our family of metal 3D printers. As I mentioned, we started with the Sapphire. Now we use a round build plate, 315 millimeters in diameter by 400 millimeters tall with two 1 kilowatt lasers. We have a version of that with a 1 meter Z height, and that is, so it's 315 millimeters in diameter by a meter tall. Same two 1 kilowatt lasers. What's really generating a lot of excitement, we first released our Sapphire XC at the end of it's been what, 2 years now, end of 2021. And that is a very large machine, 600 millimeters in diameter by 550 millimeters tall, with 8 1 kilowatt lasers. And what's important about that is you look at the throughput that we're achieving. And when you're building large parts, you really need that throughput. Another upgrade from that is the Sapphire XC 1MZ. And now with this new upgrade, we can actually upgrade XCs in the field to 1 meter Z. And the big benefit there is we're able to use swappable build modules. So we can go from green to green in about 2 hours. And that's really significant when you're working with powders such as GR Cop that take a long time to cool. I mean, they could take up to 3 to 5 days on a very large part. So we're very excited, and we see if anyone would be interested. In fact, we just had Lyft out at our facility to take a plant tour. I'd like to invite anyone who's interested to do that. It's a phenomenal facility where we have cells lined up with machines in process of being built. So it really gives you the opportunity to look under the hood. We're very open, and we want to show you what we're doing. This is the first part we printed on the Sapphire XC. We've got a lab where we have 6 Sapphires, as well as our Alpha Sapphire XC and our Beta Sapphire XC. This is a large part. I think it's about 500 millimeters in diameter. It's a diffuser, and we're very, very proud of this part. This was early on. I'll show you some other photos of some very large parts. This is a muzzle brake, and what I like about this, the picture on the left with one of our engineers, Ryan Askew, gives you a real sense of how big this part is. And this, to my knowledge, is the largest laser powder bed fusion part that's ever been printed. Next slide, please. This is a part that Kyle and I are very excited about. This is a regenerator from the Chrysler turbine car. Now, the story behind this is Jay Leno saw this car originally at the World's Fair in New York when he was a kid. He always wanted one of these cars, and he had an opportunity to buy one of the cars from the Chrysler Museum. He drove it around for a little while, but because it sat in a museum for 30 some years, some of the seals went bad and he burned out the engine. So he turned to one of our customers, Williams International, to rebuild the engine. And the reason he did that is because Sam Williams was one of the original engineers in the Chrysler turbine car. So they're in the process of rebuilding the engine now. But as you can see, this is a very large part, very intricate. It's a work of art, really. And they've got both of the regenerators in house now, and they're just getting ready to put the engine together. And when they do, Jay's going to come back out. He was out for the Woodward Dream Cruise. He's going to come back out, fire up the engine, and told me he'd give me a ride in the car. So I'm pretty excited about that. Some of the other parts we do is where our focus has always been is parts that control fluids or transfer heat. And why is that? It's because those parts are very difficult to print. And in most cases, other laser powder bed fusion companies can't print them. So we started, as I mentioned, in the space industry, but it really, that same idea transferred over to automotive with high pressure die cast tooling. Now, as high pressure die cast tools get bigger, like Tesla's got the big giga presses, the inserts get larger, And as a result, the cooling channels need to be larger. Conventional metal AM is good to about 5 millimeters. We can go up to 100 millimeters in our cooling channels. But we do a lot of different parts, shrouded impellers, heat exchangers, choke valves, and rocket thrust chambers, as well as vessels. So that's what we really like to focus on. High volume or low volume, high mix parts, which are ideal for laser powder bed fusion. And we've got a lot of innovation in the works for throughput increases that we will gladly share with you in the coming months. And with that, I'm going to turn it over to Kyle Harbaugh.
Thanks, Paul. It's a great overview. I'm going to try and do the best I can. We'll dive a little deeper into how we do these things and try to answer the question, how are Velo 3D's large format printers revolutionizing mission critical manufacturing? So I think there are 4 key components to be successful at answering this question. First, you have to simplify the process and remove variables. Second, you need a clear path to a truly scalable production. Repeatability is not only important for a single machine, print to print, but across an entire fleet of printers. Third is a mature material database and process documents. That database must be one that the certifying bodies will accept and that engineers can use for design allowables. And last, provide unmatched customer support from experts in the industry. Direct access to experts to help you through the process and accelerate your success in AM is critical. How does Velo 3D simplify the process and remove variables? Well, we offer, as Paul mentioned, a fully integrated metal AM solution. That includes the Flow, our preprint software, Sapphire, our family of printers, and Assure, our quality validation system. It's extremely important to note that there are individual solutions available in the industry, but it's how Flow, the Sapphire family of printers, and Assure interact with each other that truly enables our customers. The Sapphire machine would be useless without Flow, and a quality part does not exist without Assure. Flow is really where all the magic happens. We import native CAD as opposed to STL files, which introduce their own inconsistencies to the process. Because Flow can now detect features from native CAD, it can be strategic in how it applies its processes. Instead of just applying processes to the two-dimensional slice, Flow is taking into account the geometry that is above and below the current slice to apply its parameters. Flow is able to use tailored parameters that are unique to the capabilities of the Sapphire family of printers, further expanding on capability and repeatability. Once that slice file is prepared, it's encrypted, and all of the contents required to complete a print is contained in that print file. That print file goes to our Sapphire family of printers. As Paul mentioned, we have 2 essential machines, our Sapphire and our Sapphire XC. They all use the same software, the same hardware, and the same processes. Critically, the same lasers, just 2 versus 8. And our goal here, once again, is to simplify the process and to remove variables. The more consistent our machines are, the easier you can expand on them. And lastly, Assure. Velo 3D's Assure software compiles all the data that's produced throughout the build and presents it to the operator or customer in a digestible manner. We have real-time monitoring, real-time machine fleet tracking, live build progress monitoring. We have an automated system calibration that does not need any human interaction or physical tooling to be present. We have in-process monitoring that constantly monitors our optical health, our powder bed quality, and our build chamber environment. I want to make very clear that our machines are not closed loop controlled. The process is not altered from the build file at all. It's just there to monitor it as it goes through the build. And finally, it produces a build report, which is essentially a PDF file, a few pages long, that gives you a summary, or gives the customer a summary of where the status of the machine started in, what we've monitored through the entire build, and the result at the end, which is really critical in delivering a quality component that comes off of a printer. So that's how Velo 3D has simplified the metal AM process and reduced its variables. If you remember, the second topic we discussed was scalable production. Let's discuss how we can guarantee repeatability across an entire fleet of Velo 3D printers. So Velo 3D is often criticized for being a black box or preventing customers from changing the process. Our number one goal is to scale metal AM, and the only way to do that is to make sure all of our machines produce consistent parts, and this starts with controlled parameters. These are a qualifiable set of generalized parameters. They're driven by real-world applications over time with industry leaders and consistently generated pedigree data on material properties. Once again, this is super critical to producing repeatable results across the network. I do want to note, though, that we have encountered customers that want to develop their own, and this year we are going to be releasing a parameter editor to those types of customers. We are not a black box. We just have a common goal of producing, once again, consistent parts and scaling AM. But to those that want to develop their own, we will be delivering a tool that they can do so. So now that we have a standard fleet, let's make sure that they're all calibrated. The Sapphire includes a number of one-click, self-contained calibrations that do not require ancillary sensing equipment. The automated calibration sequence is quick enough that we suggest our customers perform it weekly to ensure they are always in calibration. It monitors optics, sensors, and powder bed quality and displays the data directly on the dashboard for all of our printers. This calibration and standardization is the heart of what makes our system truly scalable. With our standardized fleet, and now that they're calibrated, all that's left is to monitor the build for any anomalies. That's what this dashboard does for us within Assure. It monitors the peak height. So our powder bed is unique. We use a non-contact recoder, and we measure that surface before and after every layer. That's so that we can monitor both the health of the powder bed and to see what types of protrusions we're seeing. So that's what's depicted in our peak height, the very highest part on our powder bed. We also monitor our oxygen level, recirculation filter, which is just the delta P across the filter to see if it needs to be replaced, our dew point, and remaining powder. Large format printers require multiple lasers, and how those lasers interact is critical to the quality of the platform. Velo 3D takes a very unique and robust approach to this. Why is laser alignment important? So as you print, the machine and the environment start to heat up and things start to move. We're able to measure and correct for that movement throughout the entire build. If you do not correct for that, you can have instances where you have porosity and weird mechanicals that are in those stitched regions, and Velo 3D has virtually eliminated that issue. You can see in the picture on the right-hand side where we've turned off this alignment, and clearly you can see where the second layer starts second laser, excuse me, starts printing. And then on the right-hand side, that is with the laser alignment turned back on, and virtually you can't see anything on that part. You really know you have a Velo 3D part in your hand if it's big and you cannot detect any stitched regions. And that's just a testament to how good we are at correcting for this drift. So the proof is in the pudding. The following slides are a direct result of standardizing our machines, calibrating them often, and monitoring the build process. Our entire build plate is usable. We have very consistent mechanicals across the entire area. There's no dead spots, and we get really, really good results. We're also consistent across the Z height. I think this slide is actually better to depict how well we are at stitching. This was printed on our standard Sapphire 2 lasers and a full 1 meter tall build. We printed 6 coupons, a full meter height. The 2 green coupons are with laser 1, the blue coupons laser 2, and then the gray or brown coupons are with our stitched region. Those were cut into 100 millimeter sections and then pulled. And as you can see on the right-hand side, you virtually can't even see the difference between either one of our lasers or the stitched regions. Just another testament to how good we are at that stitched location. We talk consistency, machine to machine, and over time. This graph depicts 9 systems over 3 months in full-scale production. And you can see how consistent those material properties are. This was customer data, so it was diluted, and we also didn't take out some of the outliers. It was determined that those probably broke in the gauge section, so it was an outlier, especially with how they compare to the rest. But once again, we want to be transparent and produce the data as it was given to us. So you can see kind of the consistency that we see, not only once again across our machines, but also over time. And the last thing, to remove variables. So I touched on it briefly, but when a Velo print file comes out of our Flow software, it contains all the information needed to produce a part. The machine doesn't have to take that data and regurgitate it to make it printable. It's all in that print file. And so what that enables us to do is take that print file that was generated in, let's say, California, and ship it to Ohio and put it in a different machine and hit print and get the exact same results, because we know that machine in Ohio was calibrated the same way. It's made with the same hardware, uses the same software, and now it's used the exact same print file to produce the exact same result. So this really is where we unlock our scalability and allow our customers to grow. So what's scalability without a network? We have machines globally that our customers can use. And once again, you'll expect the exact same results, both dimensionally and mechanically, if you're using that same print file across all those printers. So what's next? So a mature materials database and process documents. So we've been working with leaders and governing bodies for years, trying to develop this and really push the industry to something that's common. A standard MMPDS print consists of a whole bunch of tinsel bars. Usually we try to do 3 lots of powder, no virgin powder, 3 printers, 3 different sites, 3 different heat cycles, etc. A lot of this is driven by MMPDS kind of direction. We have submitted to MMPDS before their volume 2. We hope to be published in their volume 2 as well when that comes out. But due to some of those delays and us being a little ambitious, we've pushed into other or pushed for help with other organizations. We work very, very close with NASA. They are guiding us on materials and different tests to use, as well as actually performing those tests for us. So that's done by a third party and will be made public. We're starting to work really, really closely with NIAR to get into their NCAMP database. NIAR is unique because they also produce process documentation that essentially outlines cradle to grave the entire AM process to make it repeatable. And so we hope to have data processed through NIAR also available soon. And API for the oil industry. We've worked with them and have active programs going on where customers are getting certified through API 20S. So once again, working with governing bodies to make sure we're producing good results and results that people can actually use in industry. We have a pretty decent list of materials available to our customers, noted here: Inconel, copper, aluminum, titanium, Haynes, stainless, our tool steel M300, and then we should have a 316 coming out soon. I mentioned before that our processes were typically closed. Once again, that was to unlock that scalability. But for people who are interested in developing materials of their own that are not on this list and may not be on a list that we're interested in pursuing, we will help those customers with their own parameter editor, develop their own material for their own use, with full support from Velo 3D and our applications team. So that is coming soon too. And last but not least, I think probably the most important thing that we can do to solve this problem is to enable our customers' success. So when you work with Velo 3D, you once again have full access, whether you own a machine or not, free of charge, to all of our engineers and all the support you need to print parts as a customer and end user, or as a contract manufacturer to be successful for your customers. That comes from concept review. We evaluate parts. If we find something that won't be successful or may not be successful or will be of risk, we'll go ahead and we'll do a de-risk print. Once again, just to make sure our customers are successful. We recognize that we will not be successful unless the industry fully adopts metal AM, and that's why we've really pushed to support everyone that we can to adopt metal AM, use the extra advantage of going with Velo 3D and be successful. I think Paul has kind of a little bit to add to this, so I'm going to pass it back to him, but I think that's probably the best part of Velo.
Well, first off, whenever I talk about Velo 3D and go through a process like this, people will say, well, what allows you to print these complex parts, these low overhang parts, features without supports? And I wanted to, before we talked about the support, let Kyle specifically point that up, address that.
I'm sorry, Paul, I missed it.
Well, with regard, what allows, how does Velo able to print these complex parts?
Sure.
Where other OEMs cannot? What differentiates Velo?
Yeah, and as I mentioned earlier, so it's really delivering that end-to-end solution, that metal AM solution that includes flow and our Sapphire family of printers and quality assure. So our printers have very unique hardware. We have a non-contact recoder. This enables us to print geometry that otherwise would be impossible with a hard recoder or cause problems with soft recoders. And it's that hardware that enables us to print unique things, but without flow understanding the capabilities of our hardware and then applying parameters to do so. It's really that marriage between flow and Sapphire that enables us to print those crazy complex geometries. And then to have full access to flow and be able to alter not just power, but our laser assignments and directions. We can do extremely unique things with the lasers to produce the geometry that we want. And that, once again, without owning and developing flow and without developing our own parameters that are unique to the hardware, we just wouldn't be able to do that.
Yeah, thanks, Kyle. Yeah, I wanted to talk a little bit about the something that I think is a major differentiator with Velo. I've been involved with additive manufacturing since 2005. Prior to that, I worked at a manufacturing company. And what I've seen from an OEM support is very unique in the industry. We have a ratio of 2.5 to 1 machines to field service engineers. We have weekly meetings with the customers. We have a very large team of applications engineers that helps all of our customers, and that's free of charge. It's not our machines are sold as one complete unit, and that includes our front end software, our flow software, our hardware, and our back end quality assure validation software. We don't break things up. And what I'm hearing in the field all the time, and for the last 20 years, is People will buy a machine and they simply just don't get the support they need to run these machines. These are very complex machines, and one of the things we've done is try and eliminate some of that complexity in operating machines successfully through our software. So that's one thing I really wanted to point out, because that's my first week with Velo. That's the very first thing I noticed. Okay, and with that, we are happy to take any questions anybody would like to pose, and thank you for your time.
Well, good afternoon. Thank you again, Paul. Appreciate the very robust and clear presentation. We do have a few questions that have come in, and I hope you are ready to answer those questions.
Thank you, Christine. I think we're all set.
All right, so one of the first questions, again, thank you for the clarity and the complex machines and the software and the capabilities that Velo has. Appreciate that. So one of the question is, how does additive manufacturing technology differ for different types of companies versus like space versus energy? Is there a different, and could you kind of explain what that means and how we should think about that?
Sure. Here, I'll step in. I tagged in for Kyle here. My name is Sid Rajay. I'm Kyle's counterpart in the Southwest region. But that's a very good question. I think the way that I understand it is, what is different across different industries when it comes to AM? I think when you look at the engineering fundamentals, it's fairly similar, right? In terms of, you've got complex high value geometry that is serving a purpose. So from a design side, similar reasons for using AM. Manufacturing and supply chain, also similar, I would say, in terms of reducing lead times and making your supply chain more distributed. So those are the type of reasons where different industries will go about using AM similarly. Where they differ, I think, is the level of rigor that comes with qualifying and inspecting parts. So for something that is going to be inside of like an airplane engine, for example, you would expect that industry would go through a lot more rigor for testing and understanding process inputs and sensitivities and stuff like that, versus a different industry, like maybe like an automotive industry, where additive is being used for tooling. Parts may be less critical, right? So maybe the qualification requirements are a little bit less stringent. So when you start to think about what's similar and what's different, right? In the similar category, I place the supply chain challenges and the engineering performance challenges. In the difference categories, I think I would place the level of rigor with which these processes are qualified and implemented.
Thanks. Paul, would you like to add anything, or are you good?
Yeah, I mean, we started in the space industry with unmanned flight, and it's a little bit more of a Wild West feel. When you get into manned flight in oil and gas and some defense applications, there's more certifications and qualifications involved. And then other industries, like Sid mentioned, with automotive, with high pressure die cast tooling and injection molding tooling, there isn't any qualifications other than customers' internal certifications.
Yeah.
Well, that sort of leads into the next question. So you talked about the different industries and how they can be different, but how do you go about qualifying a new material for AM? Can you expand on that?
Yeah, of course. So I think the context of this question is a little bit different than the previous. I think it's important to distinguish between qualifying a material versus qualifying a process for production. When we talk about qualifying material, right, what we mean by that is, hey, we've got a new material offering that can be printed on our system, right? And so for us, the way we differentiate ourselves in that is that we offer parameters that are ready to print parts today, right? So what you're not going to see with Velo is you won't get a base parameter, right, that just is capable of essentially building test coupons that you have to essentially build off of yourself and figure out how to do parameter development and make it production worthy. But what you will get with Velo is a parameter that's ready to print parts today. And right on top of that, and we kind of use the industry as a leader for our process development efforts. If that parameter can't do what you need it to, then come back to us, right? We'll help you develop that process to hit your part requirements. And the benefit of doing that, right, is that you're still maintaining the scalability of the process, right? In other words, as this parameter matures, right, as a function of customer need, that process is implemented across the fleet of machines. So you're maintaining your supply chain and your manufacturing scalability when it is time to go into production. So long story short, what we're trying to get away from is this historical approach of bespoke part-specific parameters. What we're trying to move towards is a scalable, controlled set of parameters that realizes the vision of a digital inventory and a distributed supply chain. Now, as Kyle mentioned, right, there are some customers with highly specialized needs that do want to do their own thing, and we have that offering coming as well, right? So this way we kind of maintain the original vision of scalability, but also give the optionality to go super custom if they want to.
Thanks for that, Sid. Paul, any response to that? Or I've got some more questions coming in that I'd like to throw out to you.
No, Sid hit the nail on the head.
Okay, so you've talked complexity, reliability. This actually is, how do you ensure confidence and reliability for 3D printed parts? You probably answered it in some of your previous answers, but what types of recalibrations are needed? Is it a lengthy process? Can you respond to that one?
Sure. Yeah. Okay. So there's two aspects to this, right? To ensuring repeatability. The first part of this is the process itself. So when you take the build file from a 3D space and convert it into a 2D slices, the output out of our build prep software flow is a file that contains the laser paths, the laser powers, everything that the machine needs in order to execute that print, okay? So that's the print instructions. And so this file is kind of locked in, self-contained, and it's ready to run on any Velo 3D hardware system, so any Sapphire system that's running that alloy, right? So that's the first half, is the actual print file. So it's the instructions that the machine needs. Then on the machine side, right, we understand that there are things like manufacturing tolerances, right? Each machine is going to be a little bit different. And so in order to combat that, right, we have incorporated automated self-calibrations. And so what that does is it takes the variations within machine to machine and essentially normalizes them and removes the effect of them, right? And that is what makes sure that every machine is at the same starting point. So now when you combine your print file, right, your set of instructions on how to execute the print with a calibrated system, right, that's self-calibrating, right, so no operator dependencies, nothing like that. You combine those, you get a recipe for repeatability that again is realizing this vision of a digital inventory and a distributed supply chain. And then in terms of how long those calibrations take, of course, there's variations between the larger Sapphire XC platforms and the smaller Sapphire platforms, but they're on the order of just a couple of hours and not like a full day, right? And what that does is it takes your calibration intervals down from what's normal in AM, right? Which is like, I think 90 days or something like that. Every 90 days, you're supposed to calibrate systems, or maybe it's best practice, to when you have a system that does it by itself, right? It's shortening that interval to just a couple of hours. And now you can run calibrations between every build if you need to. So not only are we enabling this distributed supply chain capability, but we're also shortening the time that it takes to calibrate these systems so that if you need to, you can do it more often.
And I think what's important to point out is that they are push button calibrations. We don't use external hardware to do that. So it's done by the operator. And we've got a number of case studies and a number of examples where our customers were able to take advantage of distributed manufacturing and outsource parts to our contract manufacturing network.
Yeah, that's a good point, Paul. And I always like to tell to reiterate, right? I mean, as part of the business development team, my job is to work with customers that don't want to purchase a machine today and help them work with a contract manufacturer that is running a Velo 3D system. And so in some ways, the ability to transfer this print file from printer to printer to printer is really what makes my job possible. And that's kind of the capability that we're counting on. So it's not like something super tricky. It's something we do every day.
Yeah, and I think it's also important to point out that our flow software takes in native CAD files as opposed to STLs.
Yep.
And it's a part of our whole system. We're not using third-party slicer software, third-party quality validation software. And again, that's the reason we sell the system as one entire unit. We don't break out the software, the hardware, and any other components.
Thanks for that response. So I have another question. When assessing the printability map of a material, what metrics do you use? And do you use energy densities or any other numbers?
Yeah, I mean, it's kind of energy density is something that you use when you're at the fundamentals, right? Of will you melt this material using a certain set of process parameters and produce a consistently dense geometry? So I think energy density is very critical early on when you're just figuring out how to melt powder. Once you've dialed that in, your core parameter, that's when you start moving into part-specific metrics, right? And I think I largely place them into one of three categories. One is going to be your geometric accuracy, so your dimensional accuracy. Number two is going to be your surface quality, so your surface roughness. And the third will be your mechanical properties, right? How strong is your metal? So those are the general sort of metrics that we use. Energy density early on. Later on, it's more part specific as we move through the process of making these parameters production ready and able to print parts.
Thank you, Sid. We have a couple more questions as we are coming to a close for this liftoff webinar today. So you mentioned Tesla's use of giga castings. I'm assuming you meant the molds. Do you have experience with printing the steels for these molds?
Yeah, that was just an example of Tesla using these large giga presses. There was no correlation between them and Velo. But yeah, it would be high pressure die cast inserts where conformal cooling channels are required.
Thank you for that. So the last one, I'd like to use AM, but for me, it's the biggest cost. The biggest barrier is cost. How could I take advantage without having to purchase a machine? Is that possible? And can you?
Yeah. I would say reach out to me or Paul or Kyle. That would be the first step. But the way that we enable customers to work with AM, if they can't justify the purchase of a machine, is to work with our network of contract manufacturers. And those contract manufacturers, right, were machine shops first. So what that means is when you go to them, right, to print on a Velo system, you won't just get a printed part, but you'll get it printed and post-processed. Post-processing is such a key part of the manufacturing process that doesn't get talked about enough. And so the idea is when you go to a Velo CM, right, you're working with them to purchase parts. You don't have to purchase a machine right away, but you're also getting a truly end-to-end solution, right, including the print and the post-processing. Anything else to add to that, Paul?
Yeah, I agree. We've got I think 8 or 9 contract manufacturers set up around the country, and Sid's group and Kyle's group has an insight into their lead times in the materials they use. So we always recommend, if you need a part printed, to go through our business development tech sales, and we can direct you towards the contract manufacturer that would fit your material requirements and lead times. And we can also do ROM cost models to give you an idea of what your part might cost, whether you had a machine in-house or whether you're using a contract manufacturer.
Thank you, Paul and Sid. That's going to wrap it up today, but I will say, well done, excellent, talking about resilient distributed supply chain, digital inventory, end-to-end, post-processing, it's important, qualification, appreciate the expertise, insights. Thank you for joining us today for this series of the Liftoff webinar. Have a great day, everybody.
Thank you, Christine.
Thanks,
Christine, for having us.